Okay, the second half of momentum is got to do with collision. So we mentioned in the previous video that momentum P is defined by mass times by the velocity, and this is a vector quantity. Now, we also established that change in P, which is the impulse, equals the force times by change in time. So this means that in the absence of any force, there is no change in momentum. Okay, so which means, and that means in an isolated system, so say in a system when there's no other force acting on something, you got one ball coming this way, the other coming that way. The total momentum, okay, the momentum of ball one and the momentum of ball two, okay, will actually be conserved. So the two of them added together, okay, before will be the same as the two of them added together after. So note that P1 will be changed by P2 after, but the two of them added together are the same. So I'm going to write a generic expression that can be applied to many cases in this case. And we'll use this equation to work out collision problems. And note that energy isn't always conserved in a standard collision. Okay, so some kinetic energy will be lost, but momentum will always be conserved. Yeah, so and that's a good thing because we can use how to work out what things are going to be. So I'm going to write in the more generic term that m v1 b for before plus m, and this is m1 m2 v1 sorry v2 b for before mass equals to, I still got my m1 v2, sorry, v1, a for after, plus m2 v2 a after. Okay, so the momentum sum before, b for before, must be equals to momentum sum afterwards. Okay, so this is in the absence. Okay, so in the absence of external force. Okay, so if there's no other force in this context, like friction, then this will be true. There will be no momentum change of the two. There will be momentum exchange, but there won't be momentum subtraction in a sense. All right, so let's look at a work example because most of the time we apply this to context. So the diagram before show a 1.5 kilogram ball moving with a velocity of 10 meters per second colliding with a stationary ball of mass 3.7 kilograms. After collision, the balls stick together. Okay, I want to find the combined velocity after the collision. Okay, so I'm going to substitute what I know in here. So first of all, the ball is 1.5 and 3.7 kilograms respectively. So I've got 1.5 mass 1 times by 10 meters per second plus 3.7 times by 0 because it's stationary initially, the velocity will be 0. And afterwards, my mass doesn't change, but we don't know what mass 1, mass 2 is. In fact, we do know mass 2, which is 3.7. Okay, but one thing we know is since the two of them stick together, then V1A must equals V1, sorry, V2A. Okay, because they have the same velocity, they travel together. So I can simplify, and I'm going to calculate the left-hand side here. I've got 15 equals to, and now since V1, the after is the same, I have 1.5 V1A plus 3.7 V2A, sorry, V1A. And since they are like terms, I can say 1.5 plus 3.7 all times by V1A, since they're the same. Okay, and moving up, then I can say 15 divided by 5.2 equals V1A. All right, so V1A equals to, I'll get my calculator up, 15 divided by 5.2 is 2.88. Have I got the rounding correct? And since 2 sig vig, this is roughly equal to 2.9 meters per second. Now I'm going to add on a little bit extra for this because we want to determine something from here. All right, so if I have 2.9 meters per second for the both masses, then my kinetic energy initially will be 1.5 times 10 squared, and that will be what would that be? 150 joules. Now kinetic energy afterwards, it will be 5.2 times 2.9 squared. So that's going to give me 5.2 times 2.88 times 2.88. That's going to give me 43 joules. So after the collision, since the two of them move together, they actually have different. We actually lost a fair amount of kinetic energy, generally due to heat. Okay, but momentum is conserved. Now, so there are types of collisions that allow you to conserve both kinetic energy and momentum. Okay, so we're gonna go through different types of collisions. So if you have an inelastic collision, okay, that means momentum is conserved, kinetic energy is also conserved. Inelastic collision is when you have one ball coming and afterwards you have this one here stationary and this one here move at the same velocity as before. Okay, and this will only occur if the two masses are the same. Okay, so after the collision, the first ball stops and the second one keep moving at the same velocity. Okay, this is called inelastic collision, and because V2, because they have the same mass and V2 is the same as V1, you have both kinetic energy conservation and momentum conservation. Okay, we also have apologies. This is actually elastic collision. So since elastic means you retaining the kinetic energy. Now, what you have, on the other hand, is inelastic collision. Okay, inelastic collision is when, say, there are different cases. So you can have the two of them, going towards each other, and they stop. Okay, you can also have this one moving, this one also moving at slower speed, and afterwards the two of them move at different speeds again together. You're not going to get full kinetic energy conservation in that case. Okay, you can also have, in the case that we had just discussed, this one coming, this one stationary, and afterwards the two of them actually move together. Okay, this one here, I also call that a sticky collision because the two of them are stuck together. Okay, so in these cases, you're not going to, hang on, let me zoom in a little bit. In these cases, okay, E is conserved. Okay, your kinetic energy, on the other hand, not conserved. Okay, all right, so that's it for this video, and there will be another one showing a few more examples to come.